Okay, this is simulating shit with Numpy. Numpy. Doesn't matter. Okay, so you wanna choose something first. You can import Numpy. Okay, I'll simulate a random number. Fuck. Okay, simulate some random numbers. Simulate some normal draws. We can do other stuff too. Um, Reading off of a blog post for full disclosure. This is pretty straightforward. Okay. Yeah, I'm using a mix of single quotes and double quotes. What of it, fam? Random walk. Now let's do some What is Brownian Motion? Firefox. Fuck. The random movement of particles suspended in a fluid or gas. This was initially generated by a botanist in 1827, Robert Brown. Albert Einstein used it. It's pretty popular in finance. It describes a motion of a system. So this is Brownian motion, right? It's doing random stuff. That's two-dimensional Brownian motion. We really only care about one-dimensional Brownian motion because that's what time series are. I really care about is this. I don't know why we're taking the square root. Let's square square root. The second movement, however, is non-vanishing, being given by the expectation of the x squared equals 2 times dt, right? And this looks pretty similar to this, where we're generating a random thing with the mean of 0 and a standard deviation of this, and we're going to generate n of them. So that all makes sense. Does it? I don't know. We'll see. And then n equals 1000 dt equals the same as above. Why are we even setting it here? Position. This is going to be a series. And gt. Okay. Just to verify. That's Brownian motion. So we can escape dd. Enter, enter, enter. Time equals impedance. Start at 0, we'll go to n times dt, and finish at n. So start, stop, number of steps. Fig here. Draw a figure of fig size equals 6. X, Y. It's there somewhere. Okay, there's some Brownian motion. How different does that look from the simple random walk? Those are different, right? They don't look very different. They're slightly different. That's different. So random walk, Brownian motion. Seems like we're headed somewhere. Monte Carlo methods. The basic principle of Monte Carlo methods is that we randomly simulate processes to solve problems that might be deterministic. For example, we could simulate credit risk by simulating the default behavior of a massive number of times to get a distribution of potential loss. The most common Monte Carlo simulation is the pi estimation, which is visually intuitive and can demonstrate the Monte Carlo principle. Now let's try to estimate pi using Numpy. We're going to estimate pi. Sam. We're going to generate x. From 0 to 1 of the times of the sample. And we're going to generate x and y. And then we're going to do the formula of a circle x and y squared. as the radius. Pi times r squared. So we don't know pi. Um, draw path. Circle, center, point. And this point is x, comma, y. And to get from here to here, we're going to have this x and this y. And then we need this d, and this d equals x squared plus y squared. In case anybody was confused. Okay, so we're getting that distance, which will give us the point. And then we're going to do this filter called inside dis, where dis less than or equal to 1 dot size. Now I'm not sure why we're doing this bit right here. We're just going to do, we're going to go with it, flow with it. Because this is just a filtered Numpy array of distances. This will make it you ever want to know what's going on inside your code, just figure it out. So let's say sample, oh my fucking god, equals 100. Run that. Could have done this inside. Okay, sorry. So this is getting the number of points that fall inside of this uniform circle, a circus with a radius of 1. Let's just continue because this is confusing me too. I'm supposed to be explaining this to you, but I'm not. Circle over sample. We'll know if we did it right. We didn't do it right. Okay, so it does it right. I don't understand this line, but look at this. I don't really care. This is how you do Monte Carlo simulation. If you don't know basic geometry like me, doesn't really matter. We estimated pi. Woohoo! Okay, now what do we do? So the code above would try to estimate the value of pi. Okay. We consider the point inside the circle if the distance is less than 1. Then we calculate all the points that fall within the circle and divide by the sample number. Got that? That makes sense. And lastly, we estimate the pi by multiplying it by 4 as the circle we have is the quarter circle. So let's go back to the drawing pad. So we haven't estimated all the values here because it's just 0 to 1. This is 1. And it rotates to here. So we have all these points in here. So to get the full circle, we have this. We also have this. We also have these two. So this times 4. In case anybody was still confused, if you're still confused, that's okay. It doesn't matter. I want to get a new sketch pad. Okay, so we're going to do some more stuff. We're gonna do something a little bit more involved now. Simplification station. It's really important to do it as simple as possible. And by simple, the least amount of typing possible. So what is this doing? It's doing this mp dot zero. Doink, 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 doink. Okay, cool. And then we're doing some for low. I fucked myself up. And then we're gonna say for period in range. So we're iterating over the loans. We're iterating over the periods. This is gonna take. What is this gonna take? It's gonna take an integer. It's gonna take an integer and a float. And we're gonna return. We don't need this. I was just saying what it takes. It takes three things. And I'm not doing this, and I'll do it after. I'll show you why I'm doing it after, because I don't know what it returns yet from just skimming the function. Let's type the function out, get a feel for it. So we're going to say if np.random.rand, this is a random number, is less than default, the probability of defaults, and then we're going to go to loan period equals 1. Okay, why did I stop? I stopped because doesn't that seem backwards to you? If this random number we're simulating is less than the probability of default, we're setting the default for that loan and period to be 1. But wouldn't it be this? That if the random number is greater than the probability of default? I think the general consensus is that it generally be larger than a small value. This p default is small, so therefore this random number would be generally larger than it. I don't know. That seems to be the best reasoning I can come up with. And then we're just going to head out of this loop instead of doing more stuff. That's the whole function. So we're going to go default rate equals np dot mean default axis equals 0. This is why I didn't want to write this before, because we're going to return defaults and default rate. Okay, so this returns two things. And loans equals, we're going to do this for 1,000 loans, and periods equals 120. P default equals 0.02. See, that's really small. And if we were saying it's greater than that default, it would always be greater than default, because let's just run this real quick. mp.random.rand. See how that's usually a large number? I mean, larger than 0.02. Less than 0.02. 1, 2, 3 out of 100, which is about what we would expect, because there's 100, so we should see about 2. We saw 3. Um, and then we gotta call the function. So default, well, rate equals sim risk and loans and periods and p default, and then we'll plot it. Okay, I'm going to rename something here, because this isn't a singular value. This is so we have this loans are this way and periods are this way. Incorrect. Loans are, this always fucks me up. Okay, so this doesn't say whether it's, okay, so the first one is this. This is confusing as fuck, and I'll go through why it's confusing as fuck. So in this example, we have a 2 by 1 matrix, which is 2 rows and 1 column. Okay, so the first item we put in is rows. The second item we put in is columns. Great. So now we know this is rows, and loans is rows, and periods is columns. Great. Axis equals 0 is the crux here. For example, if you sum along axis equals 0, you get the sum of each column. So we're looking at the sum of all the defaults for each column. Got it. That was not bad, but we get what you mean. So we're getting the periods and we're getting the default rates because there's one rate for each time step. Oh, I just farted. Excuse me. Um, and then default, we're plotting the periods, the rates, and we're going to use a fancy marker. Okay, so that's the plot, and then we're just going to add some window dressing. So we're going to run this. There's always something, you know? What did I do wrong? Defaults. It's a typo. It's a typo. Gerd. Okay, so we can see that the default rate goes down from around 20% to around 0%. And that's expected. Why does it do that? I don't know. Run it again. The simulation after all. Okay, so that's the behavior. So as the period gets larger, the defaults grow less. I would think that you would see more, but I don't know. Right? Because like over a greater period, there would be more chance of any individual loan defaulting. Um, these are both lens spaces, right? Rows, columns. rendering over the row and then the column. So that'll give us a location in the matrix. And then we're just saying if the random number is less than the default rate, we're going to say the loan defaulted. And then we're summing over the loans. We're averaging over the loans. Is there some kind of cumulative thing going on here? We have defaults, so 1,000 rows, 120 columns. And then we'll go sum axis equals 0. Make it make sense. Size. Okay, so there's 120 items in this matrix. And there was 23 defaults in the first one, 16 in the second one, 24 in the third one, and it decreases relatively over time. But why does it decrease? That's what I don't understand. Just simplify this. Simplify this. We don't use defaults again, so there's no reason to return it. Unless you're doing something like this. Why would there be more? I don't know, guys. What do we think? Move on? Understand why this would be the same even though we're sampling from the same random number distribution? Let's go back to the sketch pad. So this is what, oh my fucking gosh. Okay, we'll move you. This is what I was expecting. This is what, this is what we're seeing. Right, so default is constant, rate is constant, number of loans is constant, but we're seeing it taper off. So I'm wondering, I don't know. I honestly don't even know. Dare we ask an AI? I dare ask an AI. I don't want to leave you all hanging, and I don't think that would be fair. Okay. This code is for a simple default. I'm dumb, but that makes sense, right? Do you guys understand? So essentially, Claude was like, Rick, what are you doing? Um, we're breaking the loop if the loan defaults, meaning that for the rest of the loans, for the rest of the period, there is no more default. Like, essentially, all of these series look like this. There will only be one. Okay, I'll show it to you this way. So we have defaults still. If I could spell anything, I would be appreciated. Right, this is our defaults. What if I sum axis equals 1? What do you guys think this is going to do? Now we're not summing over the columns, we're summing over the rows. Given the example I just showed you, can you come up in your head with what you think it's going to be? I think this is going to be a A single vector of 1,000 ones, or ones and some zeros. Ones and zeros, because right, even here we're only defaulting at around 2%. So once the loan default, we're defaulting from a smaller pool. Once we're drawing from a smaller pool, there's less of a chance we'll see an outlier that's less than 2%. See, some loans never defaulted. Most of them did. So how many loans defaulted? 902 out of the 1,000 loans defaulted. That's that. I hope you enjoyed it. See you later.